long. When we think Clojure, we think functional languages oriented towards especially processing data. One of the afterthoughts, unfortunately, is often how do we visualize that data? A few years ago, D3 was kind of state of the art. But if you view it, it's kind of like basically Vega and Vega-lite have taken it as an assembly language, something very primitive, upon which a lot more rich interactions can be built. And Chris has taken the step in the community of actually integrating with Clojure, which is very exciting, which he's going to show today. Thank you very much, Chris.
Yeah, thank you. Thank you, Dave. Cool. Yeah, thanks everyone for being here. Really excited to share this work with you. A couple things about me real quick. So my day job is working at Fred Hutch Cancer Research Center. And here I build tools for HIV researchers to better understand the adaptive immune response, particularly to viruses like HIV. And by night, I am a data scientist who works on tools for participatory democracy. So basically building tools that make it possible for lots of people to listen to each other and collaborate in solving problems and sort of breaking through political gridlock. So I can talk more about that later if anyone's interested, but that's a whole mouthful. So yeah, digging right in here, data visualization. A picture's worth 1,000 words, right? You can look at data in so many different ways and try to tease apart different factors of it, but really being able to see and visualize data is often how we get this sort of visceral, guttural sense of like, what is it that I'm looking at, right? One of the, I think one of the greatest things to happen to data visualization and data science is the grammar of graphics. And this was a book that was written which describes this sort of method for doing declarative data visualizations. And the core idea here is that the grammar of graphic tries to boil down the problem of data visualization to this simple question of how do you map properties of data to visual aesthetics of a data visualization, right? So if you want to color by some property in the data, you shouldn't have to be sort of writing some imperative code that goes and pulls out all the colors and computes some stuff. You should just be able to say color by this variable, right? So this really lets us focus on the guts of the problem of data visualization and not have to worry so much over implementation details. This has been very successful. It's influenced the ggplot2 library. In fact, GG in ggplot stands for Grammar of Graphics. And so ggplot2, is an R library, which is really popular in the data science community for visualizing data. And I started using ggplot2, I think, when I first started working at the Hutch about, I think it was 6-7 years ago. And really came to love it. It really did a great job of making it really simple to build data visualizations and composable data visualizations that you could make sort of more complex as you need. Now, my understanding is that D3 itself was actually inspired by the grammar of graphics to at least some extent. And I don't have some really good references on that, but I know that at the very least, like some of the members of the community are sort of like connected, and so like similar sort of threading of ideas there. Over how to do data visualizations. There are a number of other libraries as well. You might have heard Shiny in the R community is sort of a more dynamic or interactive version of ggplot. And there's some other libraries you might see out there in the JS community that have been inspired this as well. So this brings us to Vega. Vega is this idea of the grammar of graphics as a JSON data specification. So this was built by the Interactive Data Lab right here in Seattle at the University of Washington. And it's really sort of declarative to the max, right? And what I mean by that is that it's data declarative to the max. There's nothing more declarative than being able to specify a program as just a chunk of data. And this gives us a lot of sort of nice properties that hopefully most of us as Clojurists already kind of see where we're going here, but I'll kind of spell out a little bit of the synchronicity there in a bit. So Vega is actually built on top of and compiles to D3.js. And so, right, it's taking advantage of all of the really great work there that has been done. It's extremely powerful and customizable and configurable. You can do really amazing sort of detailed, nuanced things with it. And we'll look at some more examples later on that sort of illustrate the broad spectrum of stuff that you can do with it. But one of the things that it adds on top of the sort of core ideas of the grammar of graphics and of D3 is this grammar of interaction. So this is something that the grammar of graphics doesn't really cover, is how do you interact with data and sort of pull more information out of it through those interactions. In part, this sort of requires that there be some sort of way of specifying data flow through these specifications. When you interact with data, you often end up needing to compute something based on those interactions. And so one of the things that Vega features is a grammar of interaction and data flow. Sorry, that is to say a grammar of data flow, which is part of the grammar of interaction. This, as you might imagine from me saying the word data flow, right? This has been deeply inspired by a lot of the ideas in functional reactive programming. And so there's a lot of sort of concordance here with ideas in the Clojure and functional programming realms. But unfortunately, it's not really suitable for day-to-day visualizations by itself. And the problem here is just that it's so customizable and configurable that it ends up being a lot of work to do sort of simple things. And so really what ends up being great for, though, is a compile to target. So who here is sort of a Gorilla REPL? Yeah, okay, so a few folks here. I encountered Gorilla REPL pretty early on, I think, when I first started messing around with Clojure. My first experience programming was with Mathematica, so I'm a math major. I sort of, cut my teeth in this sort of notebook style of programming where you have this sort of flow of prose where you're explaining what you're doing and sort of thinking through things, but also little chunks of code and data visualizations all sort of inlined in this kind of document flow. And so Gorilla REPL is a really great Clojure project which tries to emulate this, and the data visualization sort of aspect of Gorilla REPL is all sort of built around Vega. And this is really great because the way that it's designed, you end up being able to sort of build your own sort of custom data types that compile to Vega in particular ways, and it's able to take advantage of all the sort of composability and nuance of Vega without necessarily having to do all of the work of implementing these sort of detailed Vega specs all by yourself. So some example Vega, just so we can sort of get this out of the way. What does this stuff actually look like? This is some example of Vega. It's, again, just a chunk of JSON. We've got a lot of sort of CRUD work here to do, right? Style cell, width, height. We need to specify those, or we end up getting just a little tiny point on the page. We specify the data. Here, in this case, we're loading from a URL. This is some data that's loaded on the vega.github.io website. Specify the format, and then we get here into the marks. And so the marks are the actual stuff that we're putting into the visualization, right? And so in this case, the marks that we're putting down are of type symbol and styling as point. And we are sourcing this data from data source 0, which we loaded right here, right? And really where a lot of the meat comes down is in this encoding. So in this encoding here, we'll see that the wrappings here is sort of annoying. I apologize for that. But the stroke is being mapped to the specification of color based on the field origin. So this is some cars data, right? So this should be Japan, US, whatever sort of countries are making cars. The X the X value is encoded by the field horsepower, and the Y value is encoded by the field miles per gallon. And where things start getting a little bit messy, and where you start to see the real work and tedium of Vega is that here we start getting into the scales, and we have to start specifying for each one of these different variables that we're working with. We have to specify what's the range and what's the what kind of values are we expecting here, etc. And finally, right? Okay, so this is relatively bare bones Vega for sort of standard data visualization stuff. And what this comes out looking like is this. So not particularly anything to write home about, right? Just a bunch of points with some color, but that's fine, right? So this is what Vega does. But now let's talk about Vega-lite. So Vega-lite is this idea of sort of a higher level specification of Vega that's more sort of appropriate for day-to-day visualization tasks, right? And when I first encountered Vega-lite, right, I started digging into Vega and realizing, like, right, this isn't really good for data visualization. Is there something like this that's, a little bit more smoothed out? And eventually I did encounter Vega-lite, and it just didn't quite feel like it was prime time yet. But it had a lot of really great ideas, and I was really hopeful for it in the future. And I'm excited to say that it's met all the sort of expectations and hopes that I might have had for it. But anyway, sort of getting along here. The idea of Vega-lite is that it's sort of positions itself as both a restriction and an extension of Vega, with focus on productivity or over control. So you're not able to do all of the sort of really fine-grained stuff that you might be able to do in Vega, but you're really able to capture a lot of it. And on the side of extending, what it tries to do is make it so that the things that you can do a little bit more easily are the things that really give you a lot of power over being able to get a lot of value out of your data. At the end of the day, though, Vega-lite itself actually compiles to Vega. So right, I said that Vega is a great compile to target. Well, Vega is actually a compile to target for Vega-lite in particular. Now, one way of thinking about Vega-lite, aside from some of these kind of higher power features, is as Vega with some nice defaults, right? And it's even been sort of suggested that you could treat it as a style guide for doing Vega visualizations yourself. Early Vega-lite was a little bit limited, as I said. There was often what I found was you could do this one cool thing with Vega, and you could do this other cool thing with Vega, but as soon as you tried to combine them, everything would break down. And that was just sort of like kind of true across the board. It wasn't really composable the way that you'd want for really being able to maximize the utility of your data through the tool. Fortunately, though, I think just within the last year, it really wasn't that long ago at all, version 2 of Vega-lite came out, and it has been just amazing. Every sort of reservation that I had about Vega-lite has just been blown away. And the team has been moving incredibly fast. I think I should have written this down what the actual number is, but I think they're on 2.6 already. They've just been pumping out the versions, and when I first started messing with Vega-lite again within the last year, after I kind of realized that, they've got some new stuff here, I should check this out. I encountered some of these similar bugs where, like, I can't do this if I'm already, doing this other thing. But as soon as I had found that problem, I realized that someone had fixed it, and that was pushed up, and so I updated my version of Vega-lite, and it just worked. So they're really moving fast. They're squashing bugs as fast as they can, and I'm really happy to say that, like, it's moving in a really great direction. I already covered that stuff. So. So some example Vega-lite here. This is more or less an interpretation of the visualization we just saw. And as you can see, it's a lot more concise. For data, we just specify a URL. This is the same URL we had before. All that we have to specify to say, like, what kind of marks we're putting in the visualization is mark point. And for the encoding, to specify, again, how properties of the data map to aesthetics of the visualization of the marks, we have a much simpler sort of map specification here where we say the X value is going to get mapped to the field horsepower, Y is going to get mapped to the field miles per gallon, and the color is going to be based on the origin. So this, as you can see, is a lot easier to digest. Now, I will raise one caveat here, which is that technically this is bad form. You will get a warning if you try to run this Vega-lite code, because technically when you specify these encodings, you're supposed to say what the type of the encoding is. So you're supposed to say whether it's a numeric value or a nominal value or a qualitative value. However, Vega-lite also does some really great work trying to guess that for you. And so you can actually usually, again, for kind of day-to-day work, just trying to get a sense of some data, visualizing things, hacking around, you can usually omit that and it will come out fine, and then customize it as you wish. If you're doing anything in production, though, you should probably do the right thing and actually be a little bit more verbose. But it's nice that we don't necessarily need to. So this is what this visualization comes out as in this case. So notice that for starters, we have legend, we have axes labels, we have a grid. It does a lot of work to figure out what the sort of most appropriate grid is for the amount of data that you have, et cetera. And the color scheme, if you'll kind of go back here, one more. yeah, the color scheme ends up being a little bit more appropriate for getting a good sense of the data. However, again, I said that, as I said, Vega-lite just compiles to Vega. And so this is the actual Vega that this visualization compiles to. You'll see that, again, here, right, so the default width and height are 200, but those are easy to change. This looks a lot like the visualization we saw before, and the reason for that is that the visualization, or the Vega spec we saw before, I actually took from this and sort of pared down to the minimal sort of Vega specification that I could get to compile. It's possible you could get a little bit more minimal, but I didn't want to go too far from what it was giving us. As you can see, there's a lot more work in here. So in particular, there's a bunch more work in specifying stuff in the scales, and there's axes specifications here. It's really a bunch more stuff. So it's doing a ton of work for us, which is really great. And again, now, so most of this stuff is overwritable. You can actually go in here in the original Vega-lite specification and say that, oh, actually, I want to do this sort of thing differently to the scale, et cetera, and it will just sort of merge that stuff in with the defaults of Vega. So really great. So now we're going to sort of enter into some philosophical nasal gaving work here. So Clojure is a Lisp, right? And one of the things about Lisp that has sort of endured and been most influential, I think, in the world of programming at large is this idea of code as data and data as code. So who knows what I'm talking about here? Yeah, that's great, right? Like we all know this as Clojures because this has become kind of like part of the ethos of Clojure programming, is sort of programming around data structures. So Lisp had this great idea that like we should write our programs as data. And it seems like a very simple idea. You can credit the mathematicians for this. But it really has a lot of power. It gives us a lot. So in particular, it really opens the road for macros, which are these functions that take in code and spit out code, right? So being able to reason about code this way and run these macro functions at compile time means that we can effectively extend the language of a Lisp. And this is true of Clojure as it is for any other Lisp, right? So the language itself is extensible. And a perfect sort of example of this is the core async library, which uses macros to capture a lot of the semantic power of the Go programming language. Right, so like imagine another language where you can do this, where you can actually sort of like steal so many great ideas from another language and just put them in your own. This is really, I think, does a good job of emphasizing the power of Clojure. Another example is I think it's, what is it, Clojure match core.match, yeah, thank you. The core.match library, which gives us sort of more advanced pattern matching functionality like you might see in other functional programming languages like Haskell, et cetera. So again, like we get a lot of power out of this idea of macros. And there's this sort of idea in the realm of Lisp and the realm of macros where you sort of get to write the program you want to write in the language you wish you had to write that program, right? So you sort of get to envision like, what's the language that I wish that I had to write this program? This is sort of a really powerful thing because it lets you think at a higher, more abstract level about the problem you're trying to solve and how do I specify that problem space, okay? And it's doing this all based on the idea that code is just data. You can take that data and transform it into other data, which represents code at compile time. But a key point of this is that macros run at compile time. This is sort of like built into the whole idea of the macro, right? As the code is compiling, it's taking in the code that you put into the macro and it's spitting something else out and evaluating that instead of what you actually put in. And this is great when what you want is the ability to extend the language, but this often comes at a cost, which is that once you've put something into a macro, you're sort of stuck with that sort of construction of things happening at compile time. And so anytime you want to do sort of something dynamic to pass code into a macro, you end up having to write another macro. And you sort of get into this macro hell of like, oh God, just to like configure this other thing, I have to do another macro. And so, I mean, that's fine. That's something sort of Lisp has lived with. But one of the things that Clojure has sort of given us is this idea that we can kind of copy the same pattern, but do it more dynamically, right? So instead of just writing macros all the time, we can actually just write simple functions that take in data and interpret them and do whatever you need to do with them, right? Whether it's spit out some other data at the end or run some data visualizations or whatever, right? So this idea of data-driven programming is really Clojure's bread and butter. And if you ask me, I mean, a lot of people will introduce Clojure as a functional programming language. And while it's very true that functional programming is very important and core to the idea of Clojure and to what Clojure is, I think it's also the case that there's other functional programming languages out there, but really what makes Clojure unique is this sort of combination of data-driven programming and functional programming. I mean, does anyone have another language out there that sort of hits that sweet spot? Yeah, I'm not seeing any hands here, right? So this is what makes Clojure unique. And what this sort of leads us to is this idea that there's really a lot of correspondence here and impedance match between Clojure and Vega Vega-lite. So data-driven declarative programming, check. Functional data flow underpinnings, check. And this is maybe a little bit getting more into the details, but there's sort of a semantic data model match between the way that we tend to represent data in Clojure and the way that Vega likes to sort of ingest data. And so all of these things sort of create this really great situation where Vega is really a great tool for Clojure to use for visualizing data. And to sort of boil things down in somewhat less navel-gazy terms, right? This is just data being awesome. So when your specifications for visualizations are just data, this leads to a lot of sort of real tangible benefits. You can create Vega and Vega-lite visualizations from any language, right? I can write Vega and Vega-lite visualizations from Clojure, from JavaScript, from Go, from any language that has a natural interpretation of JSON. And so this is really powerful because it means that when we create these visualizations, we can pass them back and forth between different programs. I can create something on a server and send it to a client. There's really a ton of stuff that you can do. And all this leads to this sort of synergy there where you do work with a language like this, Vega or Vega-lite, and it sort of becomes, I don't know, it's like it has a passport to any country, right? I mean, you can take it and do anything you want with it. Where I could write a bunch of code in Clojure or ClojureScript to generate Vega and Vega-lite, and I can use that from any other language. Well, I can then pass that to any other sort of process that might be able to run JavaScript and execute that. So enough navel gazing. Let's actually get into what this looks like in Clojure. So a lot of credit here goes to Vizard, which is a library which was written by Soren Macbeth, who's the chief data scientist of YieldBot down in Portland. And it was a very simple library which has an API from the REPL, from the Clojure REPL, building data visualizations in Vega or Vega-lite, and then sending those over WebSocket to a browser. And what this gives you is this really nice sort of workflow where you're at the REPL, you're messing around with data, you're processing things, and you want to visualize, and you have this browser tab open where the WebSocket is just live and running, and whenever you're ready to sort of update the visualization, you can just rerun the plot command, and whatever new sort of Vega or Vega-lite you've created just gets sent over the wire, again, because it's just data, right? And the visualization updates. So it's upping a really nice workflow. And I found this library and was just, oh man, this is great. I'm totally into this. I'm going to use it. But unfortunately, there was sort of a shortcoming for my personal needs in data visualization. And in particular, let's get into the details of it. There are some things that you just can't do in Vega-lite. And they're working on it, and there's again, they're moving very fast, and hopefully by the time folks are viewing this this talk a few months from now, this will actually no longer be the case, and you'll just be able to use Vega-lite for the thing that initially encumbered me. But what I was looking to do was create some contour plot visualizations to do sort of density plot analysis, where you can sort of get not just a visualization of a bunch of points on a page, but something that sort of aggregates that into a sense of what's the actual underlying probability distribution here. And it turns out that this was just not possible in Vega-lite. I looked and looked and looked and wasn't, and eventually I found an issue on GitHub that sort of suggested that, okay, we're working on it, but there's a bunch of problems because of these other complications, right? So I asked if Soren was interested in adding Vega support to Vizard, and he had kind of decided already that he was not. And so I went ahead and forked and created Oz, which can Vizard Oz, right? So Oz is a library which builds off of the initial work done in Vizard, but adds support for Vega. And while I think you can certainly use Vizard, Vizard does have some ClojureScript reagent components that I believe, could import and use as sort of an API. It doesn't really advertise that, so I don't know if that's the sort of thing where you don't really know what's going to change in the future potentially. But one of the things I wanted to do was make it so that if you are sort of focused on actually building the Vega and Vega-lite on the front end, that you'd have a sort of stable public API that you could use to do that. It also has an API for composing Vega and Vega-lite visualizations together using Hiccup from the Clojure REPL, right? So imagine that you have not just one or two sort of graphs or figures that you want to look at, but also you want to be maybe putting together an HTML table or some other kind of representation of the data, some other kind of summary statistics, whatever that might be, some layout, whatever, that you can't represent with Vega itself, but that you need HTML for. Well, this is sort of meant to address that issue. And I will say here real quick that that it is possible, hopefully as we'll see here, right, it is Vega and Vega-lite both come with pretty powerful features for kind of composing very complicated plots without sort of resorting to this. And so kind of the first thing you should always do is sort of look to what's built into Vega, because you'll end up getting more mileage out of that. But at the end of the day, if you need to compose a Vega plot with a Vega-lite plot, that's just not going to be possible in any other way without some more thinking anyway. So what this kind of leads to is this ability to create dashboards or reports really simply from the REPL. Obviously, if you're on the ClojureScript side and you're using Reagent, you can kind of do this already, right? Because you're putting everything in Hiccup anyway. That's what Reagent is. And just to say one more thing about that, right? So this has a really nice impedance match in that Hiccup itself, right, is just a data specification, right? It's a very simple data specification mapping Clojure data structures to Hiccup. And so these things sort of interoperate really well. And I found it really useful to have this additional feature. And the final thing here that Oz sort of adds to the picture is plot publishing and sharing features. And this is just really simple. This was this idea that I had where the folks who built Vega and Vega-lite have this Vega editor tool, which you can go online and you can plop in some Vega or Vega-lite, and it will kind of, as you type and update things, it'll compile it for you and raise warnings if things are not right, etc. But one of the features it has, which is really cool, is that if you there's some query parameter that you can pass to the URL for the Vega editor to let it load a Vega or Vega-lite visualization from a GitHub gist. And so I built a little function that makes it so that you can when you create one of these data visualizations, you can not only visualize it, but you can actually run this publish function, which pushes that data up to a GitHub gist, and then prints out for you the URL that you would use to then load that data. And so this ends up being a really nice data sort of visualization sharing feature where I can be working on some data visualizations, and then once I have something that kind of looks nice that I want to share with someone, I can print out one of these, I can run this publish function, push that data up, and then send someone this URL, and they can load that data and actually start tinkering it with themselves in the data editor, the Vega editor. So this is kind of a nice but simple feature that adds on to the existing functionality. So for usage, setup is very simple, as you might imagine. We load the Metasaurus Oz Leiningen coordinates and require oz.core as Oz, and then run this Oz start plot server function, which opens up a browser tab with the sort of the front end code loaded, and starts a WebSocket server so that you can push Vega visualizations back and forth between, from the server to that browser tab. So the next thing we're going to do here, just for the sake of these examples, this is just a little function, group data here, which generates some random data, and this is what it ends up looking like, right? So I give some labels here: monkey, slipper, broom. You can guess how these are themed, right? And we get we get positional x values 0 through 20, and we get a bunch of random y values, and then we get this color call attribute, which points to these different values that we're passing in up in the function call above. So just some random data to visualize, right? Nothing too special here. But in order to visualize this data, we can create a very simple Vega Vegalite specification here. We define the line plot and map data to values, and then actually call this group by function and pass in the data. So you may remember from before when we were doing visualizations, the data that we were using was from a URL. So when you actually have data in process in memory that you want to visualize, you can use this values key there. The next thing we do is have the encoding. So this is pretty simple, right? We're just mapping the x to x and y to y, and then color to call. And for call, we're specifying that this should be type nominal. And then finally, we clarify that the mark type in this case is going to be line. So this is going to define a line plot now. So when we run Oz vbang on line plot, we get something that looks like this. And so this is kind of random data, right? There's nothing too special to look at here, but just for illustration purposes. So in order to do something a little bit different, for example, do a bar plot instead of a line plot, we might add some more data here. Now we've got munchkins, witches, dogs, lions, tigers, and bears. And we're specifying that the mark is going to be bar. And we're still mapping x to x, y to y. Here I'm kind of showing you what it looks like when you're doing the right thing and specifying the encoding types. So x is going to be type ordinal. And actually, I'll take a step back there. For bars, I think you maybe have to specify type ordinal. I forget. But in any case, we're doing this extra work here. But for y, we're also going to be doing aggregate sum. So this sort of starts to get us into the realm of how Vega does this sort of data flow work for us, right? All we have to do is say that we're going to be aggregating over these y values, and it just does that for us, which is really great. And so finally, color looks the same. But when we visualize this, there we go. When we visualize this, we get something like this, right? So now I'm going to kind of take a step back, and these are kind of dummy examples, right? So now I'm going to look a little bit here, share with you a little bit some of the other work that I've been actually doing with Vega and Vegalite. So this is again from the startup that I've been working on, which builds participatory democracy tools. And just to give you a little bit of background here, the tool that we built is a tool for large-scale open-ended feedback. What it does is, you start with some open-ended question, like, what do you think about, head injuries in football, or what do you think about guns in America, whatever, right? Open-ended question. And instead of having to spend all the time with a survey and generate, really sort of carefully crafted survey questions, which get all the data you need to know, you just put out that open-ended question, and people respond with comments. And then we take those comments and send them out to everyone else, right? And then those people then get to vote and say whether they agree or disagree. So based on those patterns of agreement and disagreement, we're able to do some fancy math and come up with this lower dimensional representation of this really high dimensional space. And effectively then visualize all of these points, which are small sort of groups of people, opinion groups, if you will, and these lines, which represent the comments in this conversation. And each line is sort of plotted so that it represents the best sort of approximation in this lower dimensional space of how the space of opinions are separated. That is, the space of people are separated by that given comment, right? So this isn't sort of the main visualization that we use in the tool. The actual visual, and I should have added this here, but the actual visualization that you'll see if you're using participating in a Polis conversation is one where each of the participants in the conversation you see as a little Twitter or Facebook image. And so people are closer together if they tend to agree, and then further apart if they tend to disagree. So then based on that representation, we're able to compute opinion groups and figure out what comments are most important to each group, but also where there's consensus between groups. And really what we built this tool for was, we wanted there to be a way for really open-ended, massive, distributed movements to sort of build consensus and build direction. So we were inspired by the Arab Spring and the Occupy movement, where the social media tools of the time were enough to get everyone out in the street, but not enough to bring coherence and really get people on the same page about what they wanted to do moving forward. So that's why we built this and what we're doing. I can talk all about that after the talk here, but I don't want to get too sort of carried away with that. The other thing that I've been working on, and this goes back to my day job, is this immune system Bcell Repertoire application that we've been building. And I want to point out here, Eli in the back here, he's an intern who's been helping with this and has actually done most of the work here. So if you want to actually ask actual questions about this, you can bug him. But if you'll allow me, I'm actually going to open this up and, or am I? Yeah, so this is what this application looks like. What we have here, I'm going to make this a little bit bigger so you can see. What we have here is Bcell data. So B cells produce antibodies, and antibodies are the little molecules in our system that stick to pathogens, viruses, bacteria, infections, whatever, and sort of flag the rest of the immune system, say like, hey, this thing's bad, you should remove this, right? You should delete this. But what's interesting is like the process that generates these B cells, which then generate these antibodies, is insanely complex. This is a sort of whole complicated machine for generating really diverse B cells that goes on within your body every time you get sick. And I won't go into all of the details there, but again, we can geek out on this later if anyone wants to know more. But the way I can summarize it is that there's this process which leads to the generation of what we call a naive B cell. So a naive B cell is just sort of like fresh off the mint from this kind of complicated process which generates really diverse sequences, right? But that's often not enough to really get a good sort of immune response, something that's like, can actually stick to a virus or some other pathogen. And so what follows is this process whereby one of these initial templates, these naive B cells, gets mutated by some enzymes in our body. Or this whole sort of process that goes on when you get sick, if your lymph node swells, you feel that. What's actually going on there is there's these germinal centers in your lymph node where these naive B cells are mutating really rapidly compared to the rest of the mutation rate of the rest of the cells in your body, and producing more and more diverse B cells, which actually undergo this sort of selective pressure. So the B cells that do a good job of producing antibodies that stick to whatever pathogen is infecting your body, those get reproduced more, and the others sort of die down. So there's this feedback cycle that goes on, which makes it so that those cells which do a good job of fighting whatever infection you have get reproduced more, right? And what this does is this leads to these sort of clusters of B cells that are all sort of related, that all sort of stemmed from some initial naive cell. And so when folks are looking at really massive B cell data, and I should say, like this data is stuff that we've only been able to look at for really just a handful of years now. We're only just beginning to be able to sequence B cell data so deeply that you can really get a very broad picture of what the immune system looks like in someone at any given point in time. And so this is really cool stuff to be working with. But if you're looking at this data, you don't want to just see all of these chaotic cells. You want to be able to see them sort of organized based on their relationship to each other. And what this visualization does is each one of these dots represents one of these sort of related families of cells. And when I come in here, I can sort of highlight a collection of cells. And you'll see in the table below, as I move this brush selection around, it updates the table. And this, this is a Vega visualization here. And this sort of starts getting us into what I was talking about, which is that Vega comes with this, this grammar of interaction, right? So it's actually really, really simple. It's like literally one line just to add this, this brush selection thing here. And getting the data out is also pretty simple. You just sort of attach this handler that listens to these events and spits the data out. And down below here now within this table, I'll say, so who's worked with Grid CSS yet? A couple of people, awesome, yeah, cool. So this is actually, right, you can't actually put SVGs or other kind of fancy visualizations in tables. So this is actually a grid table, which is fun. But yeah, so this is a grid table here. And what you'll see is that these bars here represent the actual naive sequences. So these initial sequences that generated each one of these sort of related families of B cells. And so we can see here this is kind of getting into the weeds here about the details of how these things are actually constructed, but the bars here represent the way in which these initial naive B cells were constructed based on the full sort of spectrum of B cells that are possible for you to generate in your body. And so as you sort of move this around, you'll see that depending on where you're looking at in this plot, you can kind of see some different patterns. Maybe these sort of green regions here are wider or less wide, depending on where you're looking. And so researchers can now use this to start digging in and figuring out which cells they're interested in finding out more about. And where this gets really fun is that as I click around here in this table and select these related families of sequences, I can actually see the evolutionary history of the sequences in those families. So has anyone seen a phylogenetic tree before? Yeah, okay, so a couple of people, right? So this is just think about this as like a lineage or like an ancestry tree, right? This sequence, this node here, this dot at the very base is this naive sequence that I was telling you about. And when it branches off up here and down here, that's sort of one lineage splitting off in this direction, another lineage splitting off, and then this one splits off, et cetera, right? So there's this whole evolutionary tree, effectively, of the B cells that are evolving in your body to stick to some pathogen. And again, so up here we can sort of really broadly look at the whole repertoire of data. But then once we're ready to dig in and actually look at a specific clonal family, I'm using the technical term there. Once we want to look at one of these little families of related B cells, we can do that by clicking there. So all of these visual components here are based on Vega and Vega-lite, and I'll say that I'm pointing at the screen here. The phylogenetic tree here, this evolutionary tree, this is based on, give credit where it's due, this is based on PhyloVega, which is a library. It's actually written in Python, but again, we were able to steal the specs because it's just data, right? So we were able to take that and put it into the application and use it for our purposes and kind of customize it. But one of the things I want to show you here is that again, like there's this grammar of interactivity here, right? So I can add these controls that do things like update the width or the height, various scalings of the visualization. And the spectrum of that kind of customization you can do is really very broad. You can really do a lot. I'm only beginning to really plummet. It's really very powerful. So yeah, and one thing I'll say about this is this is actually not written in Clojure, so I hope you don't all feel let down by that. Hopefully you can work on my boss, Eric Mattson, and convince him that he should be doing more Clojure and ClojureScript. Who thinks Eric should be doing more Clojure and ClojureScript? Yes, okay, thank you. Yeah, so his main concern, I think, is hiring. So if anyone's looking for a job and wants to talk him into it, you can help me out with that. Anyway, point being, this is actually written in JavaScript, but again, right, we're just using these data specifications. So the amount of work that it would take to port this over to Clojure or ClojureScript would almost be nothing, because most of the work here is just in all of this all of these data specifications. And so now I'm going to take a step back out here. So if you're interested in looking at the code here, we just opened this up on GitHub today. Excuse me. So if you want to see how things work here, you're welcome to follow this link and do that. The app is called Olmsted, and it's under the Matson group GitHub group. Oh, what just happened? Oh, that was not supposed to happen yet. Hold on. My apologies. OK, there we go. Yeah. So moving along, some other examples here just to get a sense of the kind of breadth of stuff that you can do with Vega and Vega-lite. Here's the contour plot that I was talking about. This is what I really wanted to do but couldn't in Vega-lite, and which pushed me towards building Oz so that I could work with Vega Data. So again, this is a contour plot, right? This sort of represents this density of points. And what's really nice about this is that if you there's not a toggle for it here, but if you turned off these contours, you really wouldn't get nearly as good of a sense, in my opinion, of the actual sort of distribution of the data. If you want to sort of visualize the data and think about it as this like sort of underlying probability distribution from which these points were drawn, this is something that this kind of visualization lets you do. That's really powerful. Hold on. Another example here of some of the interactive features of Vega and Vega-lite, and so this is specifically Vega-lite. Here I have this brush selection where I can highlight some data in one of these plots, and things cross-filter in the other panels in this plot, so that you start to get a sense via interaction of how different variables in your data relate. This is sort of this novel idea, right? That once you start to tinker with it and explore it, it really starts to feel very powerful. Where you almost start to feel, right, like you can sort of dig into the data with your hands and sort of see relationships that are actually in a higher dimensional space, right? Here we're looking at number of records based on 3 different variables. So we're sort of able to tease out these different patterns in relationship between these variables. In this case, distance, delay, and time. So any one of these that I selected will sort of show up the corresponding set of points in the other. And to take a look at the actual specification here, again, this is just Vega-lite. We don't even need the full power of Vega here to do this. And this is, again, where Vega-lite's really powerful, is that it really tries to empower us in doing these kind of interactive things. So the thing that I actually really want to point out here is that, let's see. So one, there's a repeat. So this is one of the composability pieces of functionality that we get in Vega and Vega-lite. Well, actually, I don't know that it's in Vega. I think it might just be in Vega-lite. This is where you're pushing on my knowledge. So right, what we want to do is we want to repeat the same plot for each of these 3 variables. And so we do a repeat where the column is distance, delay, and time. The columns are distance, delay, and time. And then down, let's see, down here, when we encode the x variable, we specify a repeat column, right? So whatever the x variable is going to be whichever column we're in. Very simple, right? Very powerful, though. So the next thing that I wanted to point out here is, let's see, where is it? Right, OK. So within this layer, there's selection brush, type interval encodings x. Right? So what we're doing there is we're saying, I want this brush selection of the data for the x variable. And down below, there's a transform here. So this again gets into our data flow functionality within Vega-lite and Vega, where this transform does a filter based on the brush selection. So within each one of these plots, I'm filtering the data based on what data has been selected in one of the other plots. Again, so really, I mean, this is the sort of thing where there's some details there to work out, but really this ends up being very simple for the kind of power that you can get out of a figure or out of a visualization like this. Really pretty small. That is small chunk of code, high leverage. So another example of this, and I definitely won't go into all the details of this because it's in Vega, but it's just another really cool example where, again, you start to feel like as you're interacting with this visualization, you start to see these sort of deeper relationships between different variables, exploring higher dimensional spaces. Another example here. So this is Vega does have support for Geo Data. So again, right, like you can do most of the things in Vega or Vega-lite that you can do in D3. And so this is a specification where we're looking at all of the flights from Seattle to other airports in the country. This is a little bit involved there. Part of the reason this is a little bit involved is because the specific GeoJSON form, or the specific data format here for the Geo Data is required a little bit of munging around of the data. So there's some there's a number of transformations here that it's going through. But the one that we really want to look at here is the filter. We're filtering by the field origin being equal to Seattle, or the SeaTac airport, right? So this is filtering all the data to just those flights that are going from Seattle. Where actually these things occur in a layer. So there's one layer that's just looking at the points of all the airports. And then there's another layer that's doing this transform, this filter, and looking at all of the connections between these airports, but filtering down to just the ones that go to Seattle. Right? So you could imagine that you could do this where it's not just Seattle, but as you hover and interact with this or click on a different point, you start to see different connections. So instead of Seattle, maybe you hover over San Francisco, now you see all those connections. Just to see what that might look like, we actually have a wonderful little example here. Oh, wait, hold on. Sorry, I must have missed something. Oh, here it is. This came out of order. So this sort of serves two functions, which is one, you can see that what I said here can actually be done, right? So you can move around in this plot and see different connections based on what you hover over. So the big airports have a lot more connections. We're mapping the size of these points to the number of connections that they have. And as we move around here, we really start to get a sense of how you can explore the space. So really cool. The other thing that's neat about this example is there's actually a project which, so take a step back here. Normally when you use Vega or Vega-lite, you're compiling through D3 to either SVG or to Canvas. And this is actually an example which uses a WebGL rendering plugin. So you can actually render with WebGL, which in theory for really big data should let you work with things without the kind of delays that you would be forced to work through with either SVG or Canvas. So that's pretty cool. And then the other one that I wanted to show you here, this one's a lot simpler. Actually, I should put this further up. But this is just a very simple example where we've got a bunch of data and we want to see the mean of this data. So this is precipitation in Seattle, I believe. And we want to see for each month how the precipitation in that month relates to the average across months. So as you can see, the average precipitation amount is 3. I don't know what the units are. I'm guessing 3 inches per month. But you can see that, right, this is when you want to be in Seattle, is between June and August, and pretty much the rest of the year is sort of lame. But the actual specification here that does this is, again, really very simple. So again, we're doing a layer here. We're layering 2 sort of visualizations on top of each other. The first one is the actual sort of bar chart. And the next one is encoding the y value of a rule mark, so it's just a line, as the aggregate mean of the field precipitation. And that we get is this nice red mark there, which shows us what the mean is over the data. So again, we didn't have to write code that computed the mean and then manually go in and draw some line. We just said, add this rule based on the mean of the data, right? We're just saying what to do. We're not telling the program how to do it. We're just saying what to do. So this is really cool. Now, if you're interested in a sense of really, it's really hard to pick these examples because there's so many cool things you can do. I just want to show you everything. So real quick, I just want to sort of scan through the full sort of set of examples on, I don't know if you can see the URL here, but it's vega.github.io/vega-lite/examples. And as you can see here, there's just a ton of different visualizations which show off. I mean, sometimes it's silly stuff like this, but there's really just a ton of stuff you can do. I mean, you can customize this in any number of ways towards any number of purposes. It's really, really pretty awesome. So I'm just going to scroll through this so you get a visual sense of all the different kinds of visualizations you can create. And they're all sort of organized under what sort of features they show off here. So this is a great, if you're actually interested in using this stuff, this is a great place to go to actually figure out what the heck you're doing. Reading through the documentation is very dense. Like, understanding at a deep level these specifications takes time. And I'll kind of get into that here. There's some caveats with using this, but often the best way to really move forward and learn is just to look at lots of examples and copy and cut and paste and pull. And you know, it takes a little bit of time to figure out what goes where, but you know, if you stick with it, you start to get a sense of all the details there. So again, some more different geographic displays there. Here's London tube lines. It's kind of a neat one here. Some interactive examples there. Wish I could go through all of them with you. Yeah, and then there's some links out to some community examples there. And finally, I will go through the Vega examples real quickly, just to do a sort of high-level flyby here. Now you'll notice here that you might get a sense of the kind of additional level of customizability that you can get here through Vega. So look at these volcano contours, distortion comparison. Right, you can explore different projections. If you're an XKCD geek, that might be fun. So radial tree layouts, tree maps, circle packing. These are cool, these edge bundling things. So again, a lot of this is just built on D3. Oh, U-District cuisine, that's fun. I need to look at that one. Just moved away from there, so it'll be kind of bittersweet. But yeah, okay, and so that's the end of that one. So as you can see, right, there's a ton of stuff you can do with these libraries. Yep. Oh yeah, and so one final piece here. This is sort of the coup de grace. This is a sort of Tableau-inspired data visualization tool that the Interactive Data Lab put out, which makes it possible to sort of do drag and drop data visualization. So I can drop number of cylinders into the x-axis, and it gives me a really simple visualization sort of that variable. But then if I go in and look at acceleration, now I can start to see how those variables correlate. And I'm just dragging and dropping here, right? But then if I go in and want to color by weight in pounds, I can do that. Let's see, somewhere in here. So marks auto, if I want to specify that I really want points, I can do that. Or I could do line, or there we go. Looks a little weird. Not everything's going to work out the way you might want, but right, all we're doing here is just moving things around, drag and drop. And what's great about this is all of this will just actually, at the end of the day, can spit out a JSON, right? So again, we're working with JSON here. You can use this tool to like really quickly build some visualization to gain some intuition, spit out a JSON visualization and use that, a JSON specification, and use that as the basis for customizing and building your own sort of more tailored data visualizations. And, oh wait, what am I doing? Okay. Okay, so enough of that. That's sort of a sense of the breadth of stuff that you can do. Now, just real quick, some future Oz goals. So what made the Olmsted app possible was the fact that we can hook into the brush selections, those signals that pass through the data flow graph. And that's actually not made easy yet through Oz. So that's one of the features that I really want to add, because it makes it really easy to sort of glue things together at the level of React or whatever you might be working with in ClojureScript. Also, static compilation. I think it'd be really great to be able to. So there's some details here about how this might get done, but it'd be really great to be able to run these visualizations statically, server side, and compile some visualization as SVG or PNG without having to run it through the browser. So if you kind of work on data pipelines or whatever and just want something static at the end of the day, then it'd be nice to have that possible. Also for reports and that sort of thing, nice to print out a PDF, something like that. And then, over time, it might be nice to sort of aggregate some higher level visualization constructors. I feel like I'd be remiss if I didn't sort of address some of the challenges of working with Vega and Vega-lite. I'll say that debugging is sometimes painful. This is maybe something you've already experienced working with sort of data specifications in Clojure. Right, when you're interpreting these data specifications, when things aren't right, you have to sort of figure out what's not going on, right? What's not happening correctly. And of course, in Clojure now we have spec, which is really cool and awesome. And Vega and Vega-lite are built on top of TypeScript, I think. And so they do have some sort of spec ability there and try to give you some help. But it's sometimes hard to figure out what sort of things can go where. Until you sort of dig in and look at a lot of examples, it can sort of be hard to figure out what the full spectrum of possibility is. And that really just takes time and sort of playing around and tinkering and experimenting. And over time, you do sort of pick that up, though. And the last thing, this is kind of a detail. Right, in Clojure, we often, not always, but we sometimes like to use namespaced keywords, right? So unfortunately, things don't look quite as smooth when you're using those. Instead of saying just attribute, if you have a namespaced keyword, you have to actually say datum, some whatever, right? There are the namespaces / attribute. And there are some cases where things are dynamically computed based on the attribute name, and so that's something to sort of watch out for. You might have to go through some extra hoops to make those things work. But in closing, and again, this is my last slide here. So if you have questions or whatever, we can open that up now. All the challenges aside, I'm really sold. I mean, like I said, I used ggplot for a number of years at the Hutch and was really happy with it. Really felt like this is just an amazing tool for getting lots of power out of data. But this, to me, really takes it to the next level. Between the fact that it's data-driven and I can pass things around and get all that sort of synergy, the fact that it has all these interactive features, the fact that it's sort of so in line with the Clojure philosophy, that it has so much composability and so much power and customization. And again, the interactivity of it all really make it something that, for me, is really the go-to tool now. So that is the end of my presentation, and we can open up for some questions here.
How readable is the D3 code?
That it generates?
Yeah.
Good question. I have no idea. I have no idea. Yeah. Yeah, I don't know.
I do have one more.
Mm-hmm.
Under
Yeah.
sequences, so you had a graph of number of sequences and then
Mm-hmm.
number of mutations.
Yes.
So why was there a downward trend on that?
Yeah, good question. We can go back there. Getting into the biology, huh? Let's see, wait, did we?
Was it just because there wasn't anything to mutate to?
Oh, right, of course I'm over here.
Left to mutate to?
So Eli and I were just talking about this. Part of the reason I think why over here we have this sort of set of sequences or clonal families that are really high up in terms of mean mutation is because they have this really wide green region here, which is what we call the CDR3. Really digging into the biology here, but this is the sort of most random region of this sequence that gets generated, right? And so it's the place where there's the most work necessary to A, just make the protein that comes out of this stable, but B, to actually get it. This is also the part that ends up sticking to the actual pathogen. So it's where there's the most mutation. So if you have a really wide CDR3 region, then you're going to have more mutation overall in the sequence. Does that make sense?
Kind of, yeah.
Yeah, so like let's say, right, if you have a region like this wide, which has like, 50% mutation rate, 50% of the sites are mutated. That's exceptionally high, it would never be that high, but if you just sort of imagine, or bear with me for a second, then overall the average across the whole sequence is going to be pretty high. But if you have a very small CDR3 with the same amount of mutation in that range, say 50%, that's going to average over a sequence which is, I think, these things are like 350
I see. Okay.
base pairs long, right? So the difference between like a CDR3 that's like 50 or 70 base pairs long and one that's only like 10 or 15. I don't know if those are actually reasonable numbers, but you can kind of start to see there where things would look different. So this is just the start. So one of the things we want to do with this visualization is make it so you can change what the X and Y axis are, so that you can really start to dig in and see different variables. And we're still doing work on the back end too for the data processing side to put in more data so that you know more about these families of cells. Yeah.
So you mentioned that you were an R user for a long time, and you've kind of gone in this direction towards Vega and Vega-lite. Has something else changed also in terms of sort of the statistical work that you do sort of leading up to visualization or possibly following exploratory visualization?
Yeah, that's a really good question. A little bit. Before I was actually doing much more of the analysis myself. These days I'm more building tools for the biologists to do the analysis. And so there's kind of a shift there, right? I mean, like Vega and Vega-lite are really great for building dynamic tools that other people can use. I think I would still be using this if I was doing this myself, or just kind of like dynamically doing things from the REPL. But yeah, that is something that has changed a little bit over time. Yeah.
Are you using Vega for the Polis visualizations as well, or is that something else?
Yes, and not so again, not for any of the not for anything that we sort of deliver to our clients or to the users of our application. Right now, the main visualization is in D3. So we built that a long time ago, but that was the state of the art, right? Our newer work, I think, our newer work has been in React for the sort of more detailed reports that we generate. But I think in the future, we're probably going to be going towards more Vega and Vega-lite. The stuff that I've been doing there with Polis is more for internal use, so I use it as a tool for kind of cross-checking the work that we put out for our clients and for our users, so that I can kind of test things out and dig deeper into the data. But yeah, I think eventually we're going to start using that more because it's really easy to like generate these things and stick them in a report, and that's something we'll probably be doing more of.
Is the like clustering and sort of the multi-dimensional aspect of the answers you're getting something that Vega can handle, or is that something that you have to process first and then hash into Vega?
That's a good question. There is some pre-processing that goes into that. So the way that Vega and Vega-lite like to think of data is as a, I'll use the JavaScript language because it's ultimately running through JavaScript and JSON, right? Is as an array of objects. Or if you're a Clojurist, as a vector of, or some other kind of sequence of maps. Now, it can handle sort of nested maps within that, and it can even handle sort of positional values within a nested list within that. But what doesn't work so well is when you have sort of nested data structures. So for example, for the tree visualizations, which we see down here, the sort of standard way a lot of parsing libraries will process this sort of phylogenetic data is as a nested set of objects or records, right? And that, it does not like that. So you end up having to find a way to flatten that out into some kind of list of data. So yeah, there's a little bit of pre-processing to do there, but yeah, the target is very kind of clear and well defined. Yeah, anything else? Cool. Well, thank you very much. It's been really exciting to share this. Yeah, I hope you all start tinkering around with Vega and Vega-lite.